Hello, today we'll talk about PDG, Procedural Dependency Graph, otherwise known as TOPS, task operators. So PDG is very useful, especially when it's applied to managing complex scripting chains. We'll use a few examples to show some interesting use cases of PDG and some introductory concept. A good place to start about understanding the higher level architecture and general ideas of PDG is reading up on the documentation page of on the SideEffects website. So here I have one put up. You can see there's a list of topics on the left side, and here we're just looking at one of the examples using attributes. But before we dive into this, there is actually example files shipped inside of Houdini that you can go grab yourself. So we can go there right now. If you go to, if you're on Windows, it will be under Program Files, SideEffects software, and the version of the software you're using. If you're on other systems, it will be in a similar place. Once you go in here, go to Houdini, help, files. So we're gonna grab some of the files that's in here. So the first one we're gonna get is in PDG tutorials. If you can copy HDA processor and put it in a directory you wanna work on. Then go back to files, PDG examples, and let's grab invoke and feedback HDA. Copy these two and paste it over here. We can leave this. Let's start with the first example, HDA processor. So HDA processor is a frequently used node to turn HDA you created yourself and put it inside a PDG graph and click the result. Now this file is open. You might see this warning. Just click OK and go to the desktop selection and choose Labs. So once you're here, you can dive inside. You'll start to see a little file thing here, and we can begin with this part and explain how this relates to PDG. So this GL node containing on a file path is used to display the scripting result of PDG. So if actually we navigate our right side to this location and navigate our left side of panels to tasks, topnet. I just want to first quickly generate some tasks based on the settings of this node. You'll see there are these dots created. These dots, not particularly on this node, but on nodes with actual results. If you click on this, basically what's going to happen in the background is that it changes a global definition of this PDG output string. So when this file is referring to using the syntax of @PDG output, is referring to whatever actively selected PDG file if it has an output file. Then it's going to evaluate the string attribute to the path of that file. And once that's returned into the path, basically this node is just loading that file. And since the object that contains the sub has its display flag on, even if you're inside the task operator network here, you'll be able to see the result displayed over here. And we'll see that just in a bit. But let's look at this syntax. The backtick that surrounds this is used to change expression into a literal string, because this is just a PDG attribute. Otherwise, it's an expression. It's not a literal path. The syntax looks a bit similar to vex, but in fact, it's an H script expression, and the PDG underscore is indicated that this attribute is built-in attribute. So there are several built-in attributes in PDG. If you go to the using attribute page and scroll down, you should see that there is the list of built-in attributes. And here, the one we're using is output, and it gives you a list of file names produced as output of this bit of work. So what is work? These dots you see, they represent a work item. It's an abstract way of saying that it's some job that needs to be done. And different work item just means different tasks. And the dependency that's in the name of PDG is referring to sort of the dependency between different work items. So what you see here is a very commonly used node called wedge node. What wedge node does is that it creates variations of values for certain parameters. So here you see we set wedge count of 2. That means 2 variations, and we're creating the attribute name of smoothness. And we set a wedge type of whether it be range, value list. So in range is to basically stepping the value through this range. You can enable random samples, so you can get random values too. If you do value list, you can add list of values you want to select from. Anyway, let's get back to the settings that we have here, and you'll see there is 2 values for smoothness, and here we have another wedge which is similar to this in setup, but you see there's way more work items here because we have 10 variations for body length. Then these two, when they chain together, they represent the permutation of these 2 variables, these 2 attributes. You got 2 here and 10 here. So actually, on this one, you end up with 20 because this first smoothness maps to the first 10 over here, and the second one is connected to these ones. Now, if we middle mouse and control click on one of these dots, you'll see this persistent pop-up window that this displays the attributes associated with this work item that we just clicked on. So you can see the smoothness value we'll choose here is 1, and we have the body length over here. So these are all attributes. The attributes can be inherited from the parent to the child that's in this sort of linked relationship. On the parent one, you will see over here there is smoothness of 1, and here it's inherited that attribute, even though the attribute is not created by this node. In terms of colors, the purple represents string attributes, and the green represent integer attribute, and yellow is float attributes. So wedging is a typical way you could use to toggle the parameters of your HDA and just click out different variations and see compare the result and see what you like. And as we mentioned before, you can basically, if you have more than one attribute you want to wedge, you'll basically link up multiple wedge nodes together, and they will create this sort of dependency permutation. As you can see, the wing length has wedge count of 10, so 2 plus 10 plus 10 equals 200. That's why there's 200 different items. These attributes, it's similar to these ones too. They are attributes, but they are not built-in attributes. They're just custom named and created attributes. So you can set their value range and everything, but you can see them here too. The other way you could check out these attributes, look at this node menu here. If you scroll to the right, it's hard to see. If I expand over here, you will see that. But you can also right click and click on task graph table. It's the same as that one. In the task graph table, you'll see all these entries. Each one of these entry represents what item on the current node you selected, and horizontally you can see all the different attributes that each item has, and you can see they're different in terms of the value that we're wedging. Then you can inspect what's the value combination they currently have. So you see these ones have been already clicked. I clicked on this one to click them before. Before I clicked them, they are gray. So this is a nice place to introduce the concept of static versus dynamic work items. So static work items, an easy way to understand them is that they are predictable jobs. here, for instance, we know we are doing a permutation of attributes, so we can already guess ahead of time how many jobs needs to be done. And that's going to be 200. So static work items are if you can just right click on a node and say generate in the node, and I can reverse that. If I go here and click dirty this node, that will cancel everything. Then if I go here, then do generate node, you'll see that now this node has been generated. They haven't been clicked yet. Then I can click on this one or do click node. That will it's very fast because we're not actually caching out any geometry. Right now we're just clicking the this kind of work items. So overall, there are two types of there are many types of PDG nodes, but they belong to two general categories. One is called processes. Processes, they generate work items like these. And work items generated from processes, they have a circular shape. The other type of nodes are called partitioners. So one of the most common one is called wait for all. So I'm just gonna temporarily link it up and try to click this node. Now you see this item here has a shape. It's a rectangle instead of a circle, and that's the indicator that this is a partitioner node. So what is a partitioner node? It is a way to map dependency relationships. So for instance, you need to generate something, and that thing doesn't just require a single input, it requires two different inputs. And then you have branches to click those two different inputs independently. But before those two are both ready, you cannot execute this task. So you can describe that logical dependency by using a partition node. A partition node will say you need to have two branches. It will map to the two branches and say once you guys are ready, then you can do the next stage of the clicking. So you can think of partition node just simply as sort of a dependency mapper. You could create dependency that's as I just described, as multiple things comes in. You can also do a partition node that's the reverse shape. We call it the fan out, which is sort of like the fan out kind of looks like this kind of shape, even though this is not a partition node, but it's creating extended. Like actually, I can use a better example. If I do partition expand, if I click this and click this node. Now this is sort of a fan out relationship. The symbol is very appropriate, little peas in the pea pot. So this kind of goes in and this goes out, like multiple to one and one to multiple. You can see here. That's it. If you want to divide a combination you already have into more granular subcategories that you could work on. I will get a bit more into that in a bit. Now we have HDF processes here. These nodes, along with other type of nodes, can click geometry and put the result on disk. Some of the other common ones will be rob fetch or rob geometry outputs. All these nodes can click geometry. So if you want to find out what are the common nodes you can use for PDG, there is a good one called commonly used PDG top nodes. So it's a good place to get an overview of what are the frequent ones that people be using and what they do. We want to talk about clicking and how to manage the performance of clicking. You see this local scheduler node here. This kind of schedulers, they actually are responsible for clicking, even though they are not directly linked up to the chain here. It might look as if these nodes do the actual clicking, but they are just processor nodes. They generate the work items, they just describe the job needs to be done, and this local scheduler schedule the actual processes and create the geometry. So we'll start with the regular click. if I just select this one and click it, it's going to take a little bit. And you see first there's this bright green dot says 8. That means it's starting 8 parallel processes, and they will try to cook the 200 work items using the 8 processes. It took a little bit for it to start. The green ones indicate the complete ones. If you want to see the progress, you can click on this down arrow to expand it, and that's like the cooking progress. So while it's cooking, we'll talk a bit about the HDA process and how it works. So if you look at this node, you'll see there's HDA file. So you could use this parameter to point these nodes to an HDA you have wherever you put them on the disk. Then you can typically automatically it will create this tab at the end, and this is called HDA parameters, and the interface over here is dynamically generated based on the parameters you have on your HDA. If it's not up to date, you can force it by clicking on update HDA parameters. So you see most of the parameters we just left as a default value, and we have a few parameters on the screen. So these are the parameters we're trying to essentially wedge. So here we have all these attributes created. If you look at any of these work items here, they have a combination of a smoothness, body length, and wing length attribute that will be inherited to here. So let's say the third one on this list, if we look at the third one on here, it has it has more attributes, but it has the 3 that we previously seen. Let's do a control click, and you see this is all the HDA attributes parameters that you see here, but the 3 that we're wedging is indicated over here. So you can see we're using the add syntax again, that's smoothness and body length. So the value of this will be filled up by the combination of the attribute values that's unique to individual work item. So there is 2 types of parameter value assignment style. One is called pull, the other is called push. So this is kind of a pull style of assignment, where you go to an HDA and you type this syntax of add something. Then when the work item is cooking, it will evaluate that value and assign it over there. So another possible node you might use if you do like a rob fetch, which will let you fetch a chain in the geometry context. Say if you have a grid here or something, and you want to wedge this value. Let's say we have an attribute we're created using a wedge called grid size. So what it would do is just like you do it over here, you can go to the geometry context and say add grid size, assuming grid size is the name of my wedge attribute. Then when this branch is fetched by the rob fetch, it will pull the value in from this side to that side. The other thing you could use is called a push. So in order to push a parameter is that you don't have to go to the in the great example we just saw, to type in the add syntax expression. You could enable this target parameter. I'll just open up a new one here. Enable the target parameter. I'll just bring the grid back, and you can navigate to that and specify the parameter you need. So this, in this case, rows. So this way it will push the value. Sorry, it will push the value to that side through this setting. In general, it's better to use pull instead of push, but you can read up a bit more using attribute. I think I'm not sure which page it's on. Oh, here. You can check out the more nuanced details of push and pull and what are the benefits and issues associated with each. It's not playing. All right, cool. We might have interrupted the clicking at some spot, but you see, it took a long time to click this. But here's the result that we see. When you click on any of these nodes, you see this dependency relationship, and this is mapping to all the combination of attributes using generally resulting in the final result. And this goes back to what we said at the very beginning. The reason you'll be able to see this in the viewport right now is because if you go to object, you will see that this is turned on. If I turn this off and you go back here, you won't see anything. So essentially what you see in the viewport is you're looking at this object, and this object is displaying the current PDG output file. So if you go back to tops, looking at any of these nodes, middle click it, you'll see there is attribute called output, and you see this link style path here, and that's referring to literally a path to a file on disk. And if we go here, you'll see gel, and this is all the things we've clipped. Now, we mentioned that the reason we're talking about these HDA processes, we're talking about the speed difference. If you look at this one is called batch cook. And the difference between these two, we can check out what's the difference between these two nodes in terms of the settings. Easy way to do this is like if you multi-select the two nodes, go to this labs menu here, if you have certified labs installed, and you just click on node parameter differences. So they will show you all the differences in the node palms. It's very handy to compare nodes. So this is the one that we care about, the first one, batch mode. So over here, you see the batch mode is set to off. So essentially, it's spinning up multiple different instances to click at the same time. On my computer, it was 8. If I do this one, you see instead of a dot of 8, there's only just 1. So you're going to spin up that one, then it's going to try to click using that in one batch. We'll just wait for a little bit to see the actual speed difference. Now it's going. If you remember, we took a while to click this one while we were talking about other things. Well, it's only a few seconds now. This one is completely down. So everything's correct. That's because to spin up those individual instances of Houdini actually took a long time. It's kind of equivalent to you open up new Houdini sessions. Sometimes it can take a long time. Depends on, especially if you're loading multiple packages, it will slow down the time to spin up a Houdini session. That time is much higher than the actual time needed to click one of these simple geometries. So you're actually wasting more time to open up Houdini rather than just click the results. So you can use this all item in one batch when you know that's the case, when you know your HDA actually doesn't take that much time to click, while multi-threading it actually end up wasting more time. But if the HDA you're clicking itself, it's more expensive, it takes longer time, then you shouldn't use the all items in one batch. But the more interesting one is the third one on the far right. It was services. Services, it's like using the left side, but instead of trying to create new instances every time, it will keep multiple instances of Houdini running in the background and use them whenever they're needed, because they're kept there, so you don't have to restart them every time. That removes the need to wait. While you can also take advantage of the multi instances and clicking at the same time. So what are Houdini services? So there is a description on PDG services. This one, but we're not going to read this just right now. We're just going to see that it depends on different nodes. So services currently is only supported for some of the nodes. HDA processor is the one we're going to be using. There's also rob fetch, we mentioned that before, and the Python script. So if you go to tasks and go to PDG services, you will see there is this window, and this is the services that's already here. So if I click on HDA processor service and click on start, You see this yellow right now, so it's still trying to start. Once it's all start up, it will turn green. In the meantime, let's open up Task Manager. Now you see there's a lot of Houdini sessions here now. So all these, it says Python. That's referring to one of these services. If I stop, yeah, it didn't stop yet. Let's try to stop again. Now you can see all that went away. Now it's only 4. But if I start it off again, once it's complete, there will be around 20 instances of Python. So the pool size is actually referring to how many additional persistent services instances you are creating. Currently it's set to 16. And you can create new services here by clicking on that button and choose the type of services you are creating and the name of it and the pool size. So once that turned green, we're going to try to click this one and you'll see how fast it's going to be. Okay, it's green. So let's look at this node. So to enable that, here there's a job options. Over here in the job option, if you turn it on, using HDA processor service, then you just click this one. As you can see, it's lightning fast. I think I was stuck on the last 2 for some reason. That didn't happen before. But yeah, as you can see, most of it is already done. Now if you're using a RUB fetch, for instance, it's one of the nodes that support services, and there's click type. If you set it to service, and you'll be able to use it. So that is a fluke. Typically this will be completed immediately. I'm not sure exactly what went wrong here with our demo, but it's a live demo, it happens. Just stop this. Now the next concept we want to talk about is filter. So here we have 200 items, and we know that because of the first wedge smoothness, we have 0 and 1, which means half of these have a smoothness of 0 and the other half have 1. So what if we only want to work with the results that has smoothness of here of 0? So you could use a filter by expression. So you type add smoothness not equal 0. So if you click this one, this is not actually clicking in geometry, it's just generating new word items based on the attribute values that match the expression we type. So this will isolate certain ones we have. There are other type of filters too. If you type filter, filter by range, status, and this is a useful one, labs filter by value. It's give you a better interface. You can say the attribute name you wanna filter by and what kind of filter criteria you want to set it to. So of course you can use multiple of this coming out of the same branch. Then we'll do another one. You can chain HDA processors together. For this one, if we click it, it's doing kind of a reduction based on all these ones. So there's only 100 word items down the string because of the filter. If you look at before and after, it's doing some poly reduction. Okay. Now that's the things we want to talk about using this example. Now let's move on to the second example. So if we go to top feedback HDA and launch this. Now this is opened up. Again, you have some warning. It doesn't matter. Click OK and switch to Labs Desktop. So let's see what's in the result first. Here is just another variations of displaying things. Here we have some hard-coded path. There is 3 variations of file name extensions, 1, 2, 3, and this is just trying to display 3 things together. And currently there's no result yet because these files hasn't been encrypted yet. So we go to the topnet to encrypt it. So we dive in here. We see our familiar friend of a wedge. So let's just see what he's wedging. It's wedging a shape label string attribute. There's 3 variations. So if you look at this one, there's a shape label of box, sphere, and tube. And you see this feedback loop. This is similar to a feedback loop in a way it's similar in a geometry context for loop with feedback. So what happens with for loop with feedback is the geometry, the same copy of geometry comes in and it do one iteration, it comes back to another iteration. And you know that there is the metadata import node where it contains detail attributes such as iteration, value, I value. So these things could be used to drive parameters inside this loop based on a different iteration number. And it's just sort of also like here you can see 2 HDA processes. So what happens is that the HDA will run this one, run the second one, and the result will come back, and the second iteration will begin with this again. That's pretty much how it works. You can see here there is the equivalent of the iteration attribute here. It's called a loop iter, and you can use that on the HDA parameters of your HDAs that's in here, such as here loop iter. Here's another one, and there's nothing too fancy here, just mapping to the block begin path. One interesting thing is that if we click this result right now, I'm just going to click on the wait for, this will ensure that everything will be clicked. You'll see there is currently a 3 here in the 3 green dots. What it's actually doing is that we're clicking something based on the box, the tube, and the sphere. And basically there are 3 types. So they're not running the same feedback loop. There's actually inherently 3 branches of feedback loops that are running at the same time. That's why you see a 3 here. So for each of this feedback loop, this is feedback, either the box or the circle or the tube. Once the result is done, it will be more apparent what's happening. We'll just wait a little bit. So this allows you to basically creating a branching and clicking at the same time. Because there's no dependency between the box-based variation and the sphere and tube-based variations. And while it's clicking, we can look around and see there's also a operator, a notify node is pretty handy. You can set operator path. In this case, it's pointing to this node, merge 1. And you can describe an operation you want to do. You can right-click that node, or you can say press a button. Like for a file node, for instance, there's the reload button. You can press that. We're just going to wait a little bit. I'll pause the video and come back. It's been about a minute. like an actual minute, not the expression of it's been a minute. Now let's look at what we have. There we go. So as you can see, the file name is there's a frame number here. So the frame is actually each iterations is stripped out to the individual frame numbers. If I scrub that, you can see it's evolving on itself. So this is the first iteration, the second, third, and fourth. And as I said before, these 3 branches are independently clicked. They don't have any dependency between them. So even though the task graph looks like it's just one thread, I don't know what's the correct terminology. It looks like there's one branch, but it's actually got divided into 3. And there's more description of how that's happening in the comments here. So this could be quite useful for you if you want to use some sort of iterative scripting. Maybe one of the HDA generates certain result stacked on top of the previous iteration, and you want to wedge some attribute that creates multiple branches of scripting at the same time. You can do it using the feedback loop. Now let's move on to the third and the final example, invoke. I'll just close this and go to top invoke and open up the invoke chain. Let's close that, go to apps. So let's look at the source first and see what is invoke. Here you see is a compile block. A compile block is a block of nodes that's a compilable nodes. So this operation described inside this block will be basically you can think of it as a single operation encapsulated over here, like a function. So it's not hooked into anything, but because this is just a function, you can kind of call it whenever you want it. And the way to call it is use the node called invoke compiled block. So first you need to let this this node know which function you want to call, and you can do that by dragging the compile block end node to here. Then you'll notice that at the beginning, and you have multiple inputs into this block, and each input has an input name, so you can just map the input name so that if you want to feed something here, it will know which this is feeding into. So here I'm just going to type input name of grid. Here is object. I'll put it over here. So what happens now if I hit it like this? Oh, sorry. It will be equivalent to if I hit it like so. It will be equivalent to that. But if I click on this one, you see it's being clicked. So it's a simple operation here. It's taking the grid and basically copy to the grid points. So this is how you do invoke in SOPs. A few more notes about compile nodes is that not all the nodes are compilable, but if a node is not compilable, for instance Python node, you will see currently don't see this badge, but let's see, view, actually press D here and go to the context specific badges. Here's a non-compilable sub badges, change it from hide to normal, and you'll see this little cross on a gear. That means this node is not compilable. If it doesn't have it, it's compilable. So if it's compilable, you can put it inside the compile block. That can turn all the nodes inside of it into a single operation. It's also more memory efficient because typically any of the Houdini nodes are cooked. If you inspect, there is memory. So this is these nodes are simple, there's not much memory, but you could be dealing with heavy geometry, like volume or photogrammetry geometry, then caching memories on each node can be quite taxing. Could be quite taxing on your system. But the reason it caches memory is so that you can step through the nodes and just set a display flag on any of them and quickly see the results once they are trigged. If they dump the memory, you will have to retrig them, obviously. But inside a compiler block, because we're treating this thing as a single operation, we're not really like letting you like stepping through the inside of it. Well, you can still do it, but when you do that, it will just freshly trigger whatever is needed. But if you just want to trigger a giant chain, the compiler block will just not cache memory on the nodes inside of it if it's set to here. Actually, there's a parameter for that, but by default, that's a behavior, the unload behavior always. The unload is to say like dump the memory. So when it's set to unload always, all these nodes will not cache any memory. Just off the tangent of what's interesting about compilable nodes and compile block. But the main thing we're going to talk about is how to use this inside tops. So let's go back to, I'll just keep this on the right side. And go back to tops over here. So we'll see this top invoke node, which is the counterpart to the SOP invoke. And it has a sort of similar structure too. You can add how many inputs you need. In this case, the geometry source will be upstream geometry data, because the input is fed upstream from upstream. And the block input name will be like grid or object, just like what you typed here. And of course, you need to specify which compile block you're using. And you see this is just pointing to a SOP path to that compile block. Now, how do we grab these geometries? Now here you see this relationship that goes in here to create this node. It's kind of similar to this one with a slight difference. So we're using geometry import node. So this one, it's pointing to the SOP path of this node, and this one is pointing to the SOP path of this node over here. And the geometry source is set to SOP node. One thing that's a bit different from the default value is the storage. So instead of storing it as an external file that's on disk, we're just going to store it as a geometry attribute. So there's not going to be any file, just going to be in memory. Here we have a partition node. If you recall earlier, the partition nodes, not just partition node that has a partition node, but all kinds of partition nodes, they create dependencies. What this is saying is that I want both of these input geometries to be ready before I invoke it, because the invoke node needs them both. So if I cut these, you'll see that here it creates this dependency between the two. Now it's already ready. In the advanced one, we said that SOP counting by input node order, and on the node side, partition by each input work item combination. So these two creates one. So once that's ready, we can click this invoke. So we have output, which is pointing to a specific file. That's going to display that file if we have it ready. But well, let's just do that first before we modify this node. We can click this one. You won't see anything yet because this node is also, the output is set to attribute, so it's going to be in memory. It's not going to be on disk. So if you click on this, there's no disk file yet. Here we see another one. Essentially, we're invoking it again. So that's the kind of goes back to the essence of using invoke and compile block. It's that this is not a specific set of nodes inside a rigid location in the chain. It's a more flexible function you can keep calling. So here we're calling the same thing again, but we're swapping out the input. So this structure is kind of like a, what's the word? Like fractal, a bit like a fractal of this part. So here we take the first input, still from the grid, but the second input, instead of a little platonic solid, we're taking the result of the first one as the actual input. So what we expect to see is going to be a grid of grids. So if I click this one, should be able to see it in the viewport. I maybe have turned it off. There we go. Yeah, this will help if I click the final one. So here, this is the grid of grids. If you want to see the results on this one too, all you need to do is change this to file. You can dirty these nodes, and you can set this to PDG output, and just click it. There we go. Now, let me try this off for a second. And what if we want to do some wedging? What if we want to wedge the grid size? So here, what you could do is create a wedge node here. Let's say I want to create 3 variations, and just going to call it row counts, and it will be an integer attribute, and I'll just set the range to be 0 and 10. I'll just take some random samples between these. So if I create that, now I have 3. I have a row count of 3, 9, and 3. That's not ideal. Let's find something different. 3. Try to do it again. Dirty this. Click. 4, 10, 4. It keeps looping back itself. Let's try something else too. Value list. Let's do something like 2, 5, 7. And dirty and record this. Now we have 2, 5, 2, 7. That's a bit weird. Why is it looping back to itself all the time? Yeah, I'm not entirely sure why it's doing that. Random seed. Dirty. Cook. 7, 7, 5. Huh. Uncheck that. Okay, no, that's better. I turned that off after I have the value list. 257. Now if I watch this, what I need to do is on this side, I need to tell this one to use the attribute. So here you don't see a backtick because this is not a string attribute, so it doesn't need to. There's no confusion whether this is a string or expression. This is clearly an expression, so you don't need the backtick. So now the row counts will be pulled from this side to over there when you click it. But if I click right now, you'll see there's no difference. There's a little tip given to me by Paul and Borcherson that if you go to the geometry import node, you go to the source tab and turn on evaluate with work item attribute. So here's a little bit confusing part. Is that if you look at this node, as we said before, there's this child parent child relationship, and you see that he actually inherited the row count from the parent. It does have the geometry attribute on this work item, but it's just not using it. So if you just turn on evaluate with item attribute and just delete dirty all these nodes, and right click on this one to delete the outputs. Doesn't seem to have one. Just click again. Now you see it can properly use our wedging after you turn that on. That's the end of the example files. I wanted to demonstrate. There are more from the directory I showed you earlier, and there's more information you can read here. It's a good complement to following video-based tutorials, because this gives you a very good high-level understanding of what is what and why certain things are designed in a certain way. Some of the terminology in TOPS might be a bit abstruse at first, but if you get a good understanding of the basics, then everything will start to make sense a bit more.